I'm very, very happy to welcome Karolina Dziugaite, fundamental research scientist at Element AI and very dear colleague, at one more of our guest talks at Montréal MLOpt. There's a series of talks happening roughly every 2 weeks, and we've had some good people, and we're very happy to have Karolina today. And as far as I understand it, Karolina will start by helping us understand some of the fundamental challenges in applying classic statistical learning theory in explaining generalization for neural networks. And starting from those challenges, then she will motivate, I believe, 2 pieces of work from NeurIPS last year and from NeurIPS this year that she has co-authored in collaboration with a number of people from Toronto, Vector, etc. And just one more point, we have overall an hour and a half for this meeting. The talks usually last for about an hour and a half. Sorry, what am I saying? The talks usually last for 45 minutes, but there's a lot of discussion during and after. You're welcome to ask questions during. You can type question in the chat and I will find the right opportunity to interrupt Karolina. But ideally, we'll keep the short questions for during the talk and the longer discussion for after the talk. I've spoken enough. Karolina, thank you for joining us, and the floor is yours.
Thank you. So as Ioannis mentioned, I'll be talking about generalization bounce, and in particular, I'll focus later on information theoretic quantities for producing various generalization guarantees. And most of this work has been done with my collaborators at the University of Toronto. Let me start by giving you a quick outline of the talk. So I'll be focusing on answering the question whether we can derive generalization bounds for learning algorithms based on non-convex optimization. And I'll be focusing on stochastic gradient Longitudinal Dynamics that was introduced by Tay and Velling in 2011. So for this audience, I believe I don't need to explain too much, but I'll get back to it in more detail later. But roughly, stochastic gradient Longitudinal Dynamics, or for short SGLD, updates the weights at time t, just like in the usual weight with stochastic gradient descent based on the gradient, but also adds Gaussian noise rescaled at every iteration. Roginski, Reyhane, and Togarski gave the first non-asymptotic risk bounds a few years back. So they, assuming that the learning rate eta t is going to 0 and the so-called inverse temperature parameter beta t converges, one can show that SGLD approximately samples from this Gibbs distribution, which is proportional to exponentiated empirical risk. So instead of just converging to the local minima, SGLD might be sampling around more because of the extra noise term. Also, Pensi et al. Established generalization bounds using estimates of the mutual information between the weights obtained after t iterations of training and the training set S. And these bounds are approximating this mutual information based on how much information is being clipped at each iteration of training. Now, unfortunately, these bounds are vacuous. And one could ask then the question whether mutual information can explain generalization, or is it only that the estimates used by Pensi et al. Were loose, sorry. In our work, we show how gradient noise influences mutual information, and we obtain non-vacuous bounds in a few different settings. Let me start by introducing some notation. We have an unknown data distribution D on the inputs X and the labels. For now, in the beginning of the talk, at least we consider just a binary classification setting where the labels are plus minus 1. We consider a parametric class of predictors parameterized by W. The goal of learning is to find a predictor W such that the probability that it makes an error is minimized. Of course, well, this probability of making an error is usually referred to as risk, and it's denoted by LD for the data distribution of the predictor W. In practice, we usually observe training data S that sampled ID from our data distribution. And we only have access to empirical risk, not the risk, where the empirical risk is just the average error over our training set S. We consider learning algorithms so that you can the training data S and some randomness U and output a predictor W, which is parameterizing our hypothesis. Now, to connect the risk and empirical risk, we can write down the following risk decomposition. So risk is equal to the empirical risk plus the difference between risk and empirical risk and expectation. This latter term is called expected generalization error, and I'll be writing EGE for short. So I'll be referring to this quite often later on in the talk, and it stands for expected generalization error. So consider a parametric class of neural networks. So for example, all neural networks of some particular width with, some number of layers. Many of the most successful learning algorithms look superficially like empirical risk minimization, right? So for example, the stochastic gradient descent, we usually take in a training set, some randomness, and we are trying to minimize the empirical risk directly. If we go back to the risk decomposition I just introduced in the previous slide, the expected, these algorithms that are successful, they are directly minimizing the empirical risk term. So empirical risk is small by design. Now the question that remains is what controls the generalization error, the second term? When is this term small?
That's a quick question by Simon. If it's still valid, Simon, go ahead.
Yeah. So it's just a naive question. So the way you define the expected generalization error here could be positive or negative, right? It's not the usual.
So, I mean,
like,
of course, the
it's kind of weird to have a -3 error or something.
Yeah, so the decomposition is just, of course, adding and subtracting the same term. When we want to bound this term, we usually bound the absolute value of the expected generalization error.
Okay. Simon, when you nod, she cannot see you. So, so Simon is happy with your answer.
Okay. So here's a classical generalization story. On the x-axis, as we increase the complexity of our hypothesis class H, we see that the training error usually decreases. But the test error, the true error, which is the green line, it initially decreases, and then we start potentially overfitting, and it starts increasing. The gap between the two is the generalization error. So I occasionally hear beeping, by the way. Should I be watching for any questions, or will you just interrupt me if there are any?
I will interrupt you. Don't worry about it. Yes.
Now, with neural networks, that's not really what we see in practice. So Nature et al. 5 years ago now showed that if we train neural networks, the stochastic gradient descent, as we increase the size of the network, so we increase the complexity of the hypothesis class, the training error, of course, goes down just as expected, achieves 0, and we can continue training. But the test error also keeps going down. So we don't see the overfitting we did in the classical story, just in the picture in the previous slide. And many researchers have tried to explain this, but this is still an open problem. So let W be the weights output learned by stochastic gradient descent, learning on the training set S. Now, the generalization bounce is one way to try to understand when this generalization error is small. So very often in statistical learning theory, one proves high probability bounds that take the following form. So they're valid usually for all data distributions, and they give a high probability bound that the difference between true error and training error is bounded in terms of epsilon of high probability. And this epsilon can depend on many various terms. For example, it can depend on the hypothesis class H, on the number of training samples M, delta, which is the probability with which the bound fails, data distribution, maybe even the training set, the algorithm, of course, we use, and maybe even the particular classifier that we obtained at the end of training. The fewer terms that epsilon depends on, the stronger the theory. one of the strongest theories that are out there that depend on fewest terms is VC theory. And it provides a generalization bound that depends on the VC dimension of the hypothesis class. So for neural networks, this is roughly lower bounded by the number of parameters in the network. Let's consider now a simple neural network that just has one single hidden layer and is trained on Ioannis. So it has 784 input neurons and 600 neurons in the hidden layer. So it already has more than 55,000 parameters. So this VC dimension will be even larger than that. And we know that Ioannis has 50,000 data points, right? So this ratio here will be already greater than 1. So at the end, VC theory gives us a bound that's bounding quantities that are between 0 and 1, the difference in the generalization error, but the term that's usually way larger, orders of magnitude larger than 1. It produces a vacuous bound. And of course, one could argue that as we increase the amount of training data we have, the bound will eventually go to 0 because we're dividing it by the number of training points. But of course, in practice, when we get more data, we also increase the size of the models. So as the number of training points increase, we increase the complexity of our hypothesis space, and actually we go back to this blue regime where we don't have enough data for the complexity of the model we use. So these bounds are always in this vacuous regime. And the fact that VC bounds and similar bounds based on parameter counts cannot explain generalization has been appreciated long ago. So here's a paper by Bartlett from 1998, so over 20 years ago, saying that the sample complexity of neural networks, what matters is not the number of the weights, but actually the size of the weights. So he proves the bounds in terms of the norms of the weights. And there are more recent, kind of more modern versions of this, of these bounds that were adapted for, specifically for Reyhane networks. So for example, there's this work by Nasher et al. Called norm-based capacity control, where they prove the bounds in terms of something called the path norm of the network. That's actually a scale invariant version.
There's a question regarding test set bounds, essentially. And there was a little bit of an interaction on the chat about the fact that that unknown true risk can be estimated from, let's say, a test set bound. So then Peng had a question regarding that. Peng, would you like to ask your question? Or I guess because it's a little bit technical, it involves a lot of math here that I see on the chat. Maybe we can leave it for after the talk. But maybe it's a good opportunity, Karolina, if you want to spend a few seconds to tell us whether you're happy with test set bounds, or do they answer the questions that you're asking or not?
Yeah, so they do not answer the questions I'm asking. So of course, using a test set, we can get a very, quite an accurate, probably, estimate of the true error. But of course, it's very specific for that particular case, right? It doesn't tell us when this algorithm overfits, why it overfits. If next time we train it on a data set that's slightly different, will we generalize or not, right? So a test set bound is very particular for this case and doesn't really give us any intuition why this works when it works, and doesn't give us a way to improve either. So that's why there is this desire to develop generalization bounds that depend on other quantities that would be more explanatory.
Thank you.
I'm happy to comment more on it afterwards when I know more what.
Simon has a
yeah,
follow-up.
I just wanted to clarify. So I guess so that everybody is clear. So by test set bound, you mean you evaluate your classifier on a test set, and you can then easily bound what's the generalization error of this specific classifier.
Yeah, that's right.
Which is very different than the uniform kind of bound that they have, which holds for a lot of parameters at the same time.
That's right. So yeah, a lot of uniform bounds, of course, choose a hypothesis class or subclass and uniformly bound the error for any hypothesis in that class.
All right, thank you. All right, let's move on.
Okay. So I feel like I went back. Oh yeah. Okay. So going back to kind of this form of generalization bounds, right? So I just showed some examples where the generalization bound was dependent on the norm of the weights instead of like parameter count, for example. So we can go and evaluate whether these bounds explain generalization, whatever that means, in practice. So here we trained a neural network on MNIST, I believe. On the x-axis, it's the number of training key blocks, and on the y-axis, we're tracking the path norm that the bound depends on. And we can see that it grows during training. The bound also depends on the margin. So usually the bound depends on the path norm divided by the margin. So if you have large path norm, you want the margin to be large in order to obtain a tighter bound. We see that the margin also grows during training, but note that the path norm is actually plotted on the log scale, so it grows a lot faster than the margin, leading to vacuous bounds. So here it's the true training and test error overlapping, and the green one is the bound. So initially, after maybe a tiny bit of training, when our classifier is still at the guessing rate, we have a bound that's just a little bit above the guessing rate, but just within a few iterations, it explodes and it's above 1. One could ask, what would happen if we explicitly regularize the path norm? So here are the plots for explicitly regularizing it, varying the regularization parameter. If we regularize quite heavily, what happens is the path norm doesn't grow as fast, it plateaus here, but unfortunately the margin is also a lot smaller. And at the end, we end up with a bound here that's not vacuous, so it's below 1, but unfortunately our train and test error is terrible, right? This is MNIST and it's 35%. So there's this trade-off in this particular case at least. There is this trade-off between the tightness of the bound and how good our classifier is. So in general, of course, this is just one example where people use path norm to explain generalization, to obtain generalization guarantees. But there are a lot of other pieces of work out there. And in general, we would like to show that maybe stochastic gradient descent, does X, and this X can explain generalization. And a lot of X's have been proposed. So for example, there are claims that SGD is empirical risk minimization when network is over-parameterized, or SGD does some kind of implicit regularization, does approximate Bayesian inference, and so on. But SGD is X does not explain generalization in deep learning unless X implies under real-world conditions, it implies generalization. And this under real-world conditions part is an important one. What might generalization theory offer deep learning? So one of the goals is to offer explanation of empirical generalization performance. Another thing that it may offer is prescription. It can potentially help us improve generalization, design new algorithms with improved generalization guarantees, to do model selection, which I would like to note, of course, tested bounds cannot do. Now, I would like to argue that it merely offers suggestion. So in practice, these proposed bounds lack explanation. Currently, most of the bounds are numerically vacuous, and they cannot explain generalization on their own, at least. So what a lot of people do in practice, they do some kind of empirical correlation studies to show that the quantity that appears in the bound correlates with the generalization error. But of course, it's not clear what evidence it provides for theory. I would also like to mention that we propose a way to evaluate theories empirically using distributional robustness. This is our NeurIPS paper that's just about to appear on arXiv as well. And this is joint work with Ioannis actually as well. Also, the current theory lacks prescription. So if we wanted to do model selection using the bounds that exist out there, unfortunately, it usually leads to severe underfitting. So just as I demonstrated a slide back with path norm, that when we want to regularize path norm explicitly to get maybe better generalization, we get a classifier that's underfitting. And usually some empirical work is needed to tune complexity hyperparameters, so to tune how much regularization we want to do. But of course, then, you know, again, it's arguable how it connects to theory. So one of the diagnoses is that theorists have been studying non-asymptotic bounds, but in the asymptotic limits that are not the right ones. So usually, you know, people pay attention to how the bound behaves in the number of examples, that it decreases as square root of the number of examples and so on, but different limits should be considered. For example, as I mentioned earlier, we know that as we grow the amount of data, we also grow the size of the network. So we need to look at the interaction of the two. So kind of my main point here is that we need to check theory empirically and identify the gaps in theory that can guide theory further.
A quick question.
Yes.
By Sidak. Sidak is asking if the path norm is the best norm to consider as far as we know, at least, or is the result that norm-based methods cannot explain generalization that well?
So there are a lot of other different methods proposed out there. Path norm was just one particular one that I chose to present, but yeah, I mean, generalization theory is very rich. And there, for example, that particular bound dependent on the ratio of the path norm and the margin. And there's different versions of margin proposed. So there's like all-layer margin proposed by Tenguma. It's his recent paper published this or last year, I believe. And I'm happy to talk further on related work and suggest some papers to read better.
Okay, thank you.
Okay, so what are the barriers to explaining generalization? One of the barriers is statistical. So the bulk of empirical generalization performance may be due to properties of the unknown data distribution. And of course, we only have samples, we only have access to the samples from the data distribution. Right now, the best bounds are for undertrained networks or noisy versions of networks. Is it even possible to have tight bounds for high-performance networks, or will we always have this trade-off between performance and tightness of the guarantees? Another type of trade-off is computational. Barriers are computational. A lot of these bounds depend on untrackable quantities. For example, on KL divergences, on marginal distributions, where sampling is intractable, and so on. And yet another type of barrier is analytical. So for example, we may have bounds that depend on the structure of the minima, and the way to evaluate that structure is usually done by Hessians, which of course give you a very local microscopic evaluation of the structure. But we might need to describe the macroscopic structure, and it's much harder to do by using these local estimates of Hessians and gradients and so on. Or perhaps the right bounds have not yet been invented. Let me now return to the question that I asked in the beginning about stochastic gradient and Longitudinal dynamics. Stochastic gradient and Longitudinal dynamics, we perform a gradient update on the weights at time t based on the gradient on the minibatch st, and we add Gaussian noise. So epsilon t is sampled from a Gaussian, and it's scaled by the learning rate eta t and beta t, which is the inverse temperature parameter. And as I mentioned earlier, if we just did gradient descent, right, we would be converging to this minima if our initialization was here, versus in Longitudinal dynamics, because of the added Gaussian noise term, we might be jumping to this minima instead and sampling around. So there are two views of stochastic gradient and Longitudinal dynamics. It can be viewed as producing samples from a Gibbs distribution that's proportional to exponentiated and rescaled empirical risk. Unfortunately, this is only true under somewhat unrealistic assumptions. It can also be viewed as one can also take a different view. So it can be viewed as not using too much information about the training set S. So because of the added noise, we hide some information about our training set. And the main question that I'll be asking and exploring is, does this latter view explain generalization? So let S be the training set just as before, and W the learned weights outputted by our algorithm, SGLD in this case, that takes in the training set S and some random SU. The expected generalization error, e.g. E, as I defined in the beginning of the talk, equals to the expected difference between risk and empirical risk. We'll be assuming for the rest of the talk that our loss is bounded between 0 and 1, but all the results can be easily extended to sub-Gaussian losses. Zhou-Roginsky in 2017 and other authors showed that the expected generalization error can be bounded, or the absolute value of it can be bounded in terms of the mutual information between the weights outputted by the algorithm and the training set as used for learning. So it kind of measures, the more dependence the weights have with the data, the worse the bound will be. Let the prior distribution P be the marginal distribution over the weights. And let Q denote some kind of posterior distribution that depends on the sample S. So for example, it's a distribution of the weights after T iterations of training when you're learning on the training set S. So the mutual information can also be rewritten as the expected KL divergence between this posterior Q and prior P. So for those who are more familiar with the KL divergence, this is the connection between mutual information and KL divergence. Does this theorem explain generalization of SGLD? There's, of course, one statistical barrier, that the mutual information now depends on this unknown data distribution D, so we cannot actually compute it directly. And there is a computational barrier. So even if we had access to the data distribution, this marginal distribution over the weights is often intractable, or in all cases of interest, really, it's intractable.
Can I ask a question about the theorem? So it says that essentially we want the mutual information between the learned weights W and the training set S to be as small as possible, right?
Mm-hmm.
And I'm trying to kind of make sense of that, because generally it will not be 0. Right? We're using the data to learn those weights, right?
Yes, of course. So there's an obvious trade-off here that as you're using more of the data to learn the weights, this mutual information will be increasing, but your training error will be decreasing, right?
Right.
You'll do better and better on the training set, but the mutual information will grow. Versus if you don't use the data at all, this will be 0, but of course, now you'll be performing just as well as the guessing rate. So there will be no gap between performance on the true set and on the data distribution of the training set.
Okay.
So yeah, essentially you don't want to learn too much from the training data, but you want to balance how much you take without memorization.
Okay, that sounds good. Thank you.
Okay. Let SI denote mini batches of our training set at time I, or T, I guess I should have used T. We'll denote that the L tilde a loss that's used during training, which is differentiable in our weights W. And so L tilde ST denotes the mid-batch loss on sample ST. Stochastic gradient descent makes the subjects based on the gradient with the learning rate eta T. SGLD, as I mentioned earlier, it adds an additional noise term where epsilon T is sampled from a standard Gaussian. The parameter beta T is called inverse temperature, and it trades off exploration versus optimization. Sorry. So when the inverse temperature parameter is large, will be not adding much noise and will mostly be performing stochastic gradient descent, so we'll be optimizing more. Versus when the inverse temperature parameter is small, we will be adding a lot of noise, and so we'll be exploring more. This additional noise term appearing in HLD updates makes it much easier to analyze HLD compared to stochastic gradient descent, which doesn't have this noise term added. Longitudinal dynamics can be viewed as discretization of stochastic differential equations. And again, I think for this audience, probably you don't need to go for it. And I mentioned this earlier in the talk. But you know, in the limit, it can be seen as producing approximate samples from a Gibbs distribution. When the gradients vanish, the noise starts dominating, and so we're sampling around essentially. And as I mentioned earlier, the Reyhane, or actually, I'm not sure I mentioned this, but Reyhane, Reyhane, and Tulgarsky a few years ago gave risk bounds by sampling analysis, and there has been a lot of follow-up work. So for example, we start from sequential analysis of optimization by Pensia et al., and it's been extended by various other authors, and I'm sure there are even more papers out right now. So the key is to bound this mutual information term, which, as I said, we cannot compute directly because we don't have access to the data distribution. We cannot sample from marginals. So for example, consider running stochastic gradient longitudinal dynamics from some starting point. It's an iterative algorithm, right? So it jumps around like this. And what Pensia et al. Did is, instead of considering mutual information between the training set and WT at the end of training, they decompose this into a stepwise analysis. So at each step, they assume that they know the location at time t-1, and they only compute the mutual information between the weights W at time t at the next step and the mid-batch that's being used for the update. And this is more accessible because the noise that's added is Gaussian noise. So actually, it's not too hard to show that this term is bounded above in terms of the Lipschitz constant in the worst case of the loss. So the bound that one gets at the end is takes the following form. It depends on the training time, so it sums up over all training steps t, and it grows with the Lipschitz constant L, or the Lipschitz constant L, and it's scaled by the inverse temperature parameter and the learning rate at all training times t.
There's a question by Simon. Go ahead, Simon.
Yeah, I have a notation question. I got a bit lost in the different definition. So
yeah.
QS was a distribution over the weights from a specific training set when you run the Longitudinal Dynamics.
That's right.
And then when you compute the mutual information between S and W, you had written an expectation of the KL between QS and the marginal P of W or something.
Yeah, that's right.
So the expectation now is respect to S?
The expectation is now with respect to ST-1, because that's what you use for the next update. So you only consider, now you decompose this into the sum over training times, and at each training time, you only consider what will happen in the next step.
Okay.
Okay, so instead of considering the whole, like what will happen at the end of training and thinking about that distribution, you only consider one step, and at one step, you only use a mini batch of your training set. So the expectation will be over ST-1.
So the expected generalization error.
Expected generalization error will still have the expectation over S. But now you're bounding it in terms of mutual information, where mutual information is further bounded with the stepwise analysis, And this mutual information here, the conditional mutual information, can be replaced with the expectation over ST minus 1. KL, where now posterior Q is only considering one-step distribution of the weights.
Okay, so I guess my confusion was that in the EGE notation, it looks like there's a dependence on S, but this is gone because you took the expectation respect to capital S, right?
Yes, I did take the expectation respect to S.
Thanks. Thank you.
Okay. Okay, so in Pensi et al., they bound this mutual information term in terms of conditional mutual information for each gradient step. And this notation just denotes all weights up to time t minus 1. Now, this quantity, the mutual information, this conditional mutual information is also unknown, and it's also distribution dependent, but can be bounded using Lipschitz continuity. So this approach, if you drop distribution dependence and bound in terms of Lipschitz constants, you lose distribution dependence. So you're back to distribution independent bounds. And maybe one of the things that I didn't highlight enough earlier is that in order to obtain tight generalization bounds, we actually do need to maintain distribution dependence. Otherwise, we'll be making bounds that are valid for the worst case distribution, which can be, random labels, and which doesn't have any signal. So we want distribution dependence in order to get tight bounds. And unfortunately, in Pensi et al. Paper, by bounding this conditional mutual information with the Lipschitz constant, they lose distribution dependence. And especially in deep neural networks, the Lipschitz constant for the empirical risk is very large, and it produces vacuous bounds. So here's the same bound that we had earlier by Zhu and Roginski, that's just in terms of mutual information. And consider starting at this point, let's say we know all the whole path beforehand. So this is, let's say, the weights at time t minus 1. At the next time step, we may have a distribution that produces the following gradients, or they're quite spread out, so we can go anywhere here if we sample a mini batch. Alternatively, we can have a case like this, which is, it's way less spread out, right? Essentially, if we had the data distribution access, we could predict pretty well where the next step will go. And this is what we're trying to take advantage in our work. So let J be independent random subset of some size n. Then the training set S can be split into S with indices J and S and the leftover S naught Sj. Oops. Consider the posterior distribution Q again, which is the distribution of the weights given our sample S. And now consider the prior that depends on the sample Sj. So it's a data-dependent prior now. Oops, sorry, 1 second. It's a data-dependent prior now. So it's a distribution on W's given our subset of the training data Sj. Then what we show the theorem of proof is the following. The expected generalization error can be bounded in terms of this conditional mutual information, where we are measuring mutual information between the weights W, this complement of the training set that the prior hasn't seen, conditioned on this subset of the training set that the prior has access to. Of course, we need to pay for this, right? We cannot just get data dependence and don't pay for it. And what we pay is that we're dividing by a smaller number. So in the previous batch, we were dividing by S, which is the size of all of our training data. Right now, we're only dividing by the size of the training data that was not seen by the prior distribution. Are there any questions here?
I think I'm trying to understand here again some kind of connection to test set bounds, because we're back to a situation where you have partitioned the data set, right, into a part that's used for training, I guess, and a part that's just used for you to evaluate this mutual information, if I understood correctly.
Yeah.
So is that understanding correct, first of all?
Yes, that understanding is correct. Now, I partition the data, but I will still be learning on all the training data, actually. So that's one thing I wanted to mention. In the test set bounds, the difference is that in the test set bound, you just compute this empirical estimate of your true error, right? In this case, you'll be using the training data to understand how some of the quantities, like these mutual information quantities, what do they look like?
I see. So I don't want to spoil the remainder. Are you going to end up using some of these terms as regularizers? And
so not in this work. We don't do any explicit regularization. We just run stochastic longitudinal gradient dynamics, and we are only using training data to kind of explore how these mutual information terms change during training.
Okay. Thank you. Timo has a related question, I think.
Yeah, so just a clarification question. You said let J be independent. Well, I guess there's J in. I see. So
yeah, it's independent of your training set. So you can't just look at the training set and decide I'll pick entries 1, 5, and 10, but you just choose it randomly, independently.
I mean, so the index of the training example you use is random, but it's still a subset of the training set, correct? Okay. So I guess the part I was confused. I thought you had two different sampling, but you actually have J and J bar, which are complements. So you partition in two pieces.
Yes, I should have made it clear in the slide itself. I kind of try to say it, I think, but yes, it's just partitioning the S into two different parts.
Mm-hmm.
Okay, so rewriting mutual information. Now, this conditional mutual information in terms of KL divergence, we can just plug it in the bound, and we get KL divergence between the posterior that's learning on all the training data and the prior that's learning on the subset of the data indexed by J. And this bound holds for any prior distributions P, actually. So it doesn't have to be this marginal distribution. Of course, if you choose some weird priors, the bound will become looser. So you still need to make a clever choice, but it holds for any priors. Now let W0 to WT denote the iterates during training, and define Q capital T, your a random variable, which is the weights at the end of training. So the distribution of the weights at the end of training, and T with the bar, the distribution on the weights at time T, conditioned on your training data and all the weights up to time, or sorry, just the previous weight before time T, so at T minus 1. And the priors have very similar notation. So P at capital T just denotes the prior distribution that learns on sample SG, and P with a T bar, it has also access to the weights at time T minus 1, so to the previous iterate. P naught equals Q naught because we're at initialization, so we don't do any learning. Then we show that the KL divergence can be decomposed into the sum. So the KL divergence between Q at the end of training and P at the end of training is bounded above by the sum over the training time of the expected KL divergence between the posterior and the prior that conditions on the weights at the previous time step. So this is a little confusing, but it's very similar to the stepwise analysis that was done with the mutual information by Pensi et al., but in terms of KL divergence instead. So as Jade notes, this random subset of our training set S of size M, and it's chosen independently of our iterates. Then the one-step distribution of Q of the weights given where we are right now is just a Gaussian, right? Because we were at weights WT minus 1, and we take a gradient step usually and add some Gaussian noise, right? So the gradient step just recenters our Gaussian, and we know exactly what the noise term looks like because we know by how much we perturbed our gradients at every iteration. So we have this explicit form of the our posterior distribution at time t. Then we can consider the prior p, which takes the same form, but now it's centered at, the Gaussian is centered at the weights that are based on the, only on the subset of the training data. So QT had access to all the data, PT only has access to the subset of the data. Right, so now they're both Gaussians. They both have same variances. The only thing that differs is the mean. One can set the mean based on all of the data, and everyone can set the mean only on the subset of the data. And so the Kale divergence has a very simple form. It depends on this term that we name incoherence, which is the difference between the gradient on full batch minus the gradient on the mini-batch, on this random subset of the data SG that's accessible to the prior. So does it make sense?
Yes.
Yes, okay. And the bounds we obtain are the following. So the first bound is by Pensi et al. That bounded the mutual information term at every step in the worst possible case. So it's a distribution independent bound, and they obtained the bound in terms of the Lipschitz constant L. There was some follow-up work by Mo et al. Where they obtain a similar bound, but now they have the size of the gradient instead. So instead of upper bounding into the worst case, they actually have the size of the gradient, which can still be large, especially in the beginning of training. If you ever track the gradient sizes, they're very large in the beginning of training. And the bound we obtain instead depends on the difference of the gradients between the full sample and this random subset of the data, which can be much smaller, or the norm of this.
I've got a question from the previous slide. Yes, like does our QT and PT bar independent, or it's the same Gaussian noise? It's the same.
Yeah, you can actually, so we are not looking at the samples, we're just computing the Kale divergence between the two. But because the noise is independent of your data, depending on the analysis you use, you could couple the noise. So they could have access to the same noise. But in our case, because we are only computing the Kale divergence between the two, what we care about is really just the difference between the means.
Okay, thanks.
And here are the bounds. So here we plot the size of the gradient that appeared in Mo et al. Bound in this bound. When it's estimated based on the mini-batch of different sizes. And we see that it's pretty large. I mean, these numbers are huge. And these two lines demonstrate the size of our incoherence term during training. When we use different size subsets of J. So in this case, so the held out number of points means held out from the prior. So it's the complement of what the prior has seen. Essentially N, which is the number of training samples, minus M, which is the number of the size of the subset J. So if we we're holding out 1,000 samples from the prior, we get a line that looks like here. So that's our incoherence term. If we hold out only one sample from the prior, so the prior has access to all but one data point, we get this blue line. And we, initially in the beginning of training, it's pretty large because there's a lot of stochasticity in the beginning, and the gradients vary greatly between each data point. Versus at the end of training, it kind of plateaus and really drops off. And you can see that these numbers are way smaller than the numbers that the other bounds depend on.
It's a question about N, I think the variable N, came from Simo.
N? What's the question?
Simo?
Yeah, so basically because here you say the N minus M was 1,000.
Yes.
So what was just N to get a sense of the scale of M versus
so this is just, I forgot if this particular plot is for M is for CFAR, but 50,000.
I see.
Most likely. I should double check. That's a good question. But it's possible that we use the subset, but I believe we use all the data. So but basically, it's you do much better if you let the prior see all but one data points. Because during every epoch, then you are only encountering this unseen data point once, essentially, and you're paying a much smaller penalty.
But it's a bit surprising that you would have such a difference between 50,000 minus 1,000 versus 50,000 minus 1, right? But
yeah, I do agree that it seems to be surprising. So I'll double check the details.
Thanks.
I'll let you know. Do I still have time? Sorry, I wasn't tracking.
Yes, we have another 36 minutes on our budget for this meeting. Okay. We don't need to use it all, but we can.
Yeah. So I'll use maybe another 5 to 10 max. So here are the bounds that we obtain. This is the bound by Mo et al. They depend on the norm of the gradients. I forgot actually what beta. Oh, the beta. So beta is the inverse temperature parameter, and this is just setting various inverse temperature values at different points in training. So here are the two bounds by Mo et al. For different temperature parameters, and here are our bounds, which are way smaller in scale. But of course, there's still a long way to go, right? They're way above the actual performance, but much smaller. And this particular one, I think, is for MNIST, and this one is for CFAR on a convolutional network. So I'll skip this. So let me talk a little bit about our most recent work, which is appearing at NeurIPS this year. The past iterates during training, W0 to WT, reveal information about the unknown data point that we should be able to use to make better predictions at the next time step. So in our previous bounds, we just took the knowledge that we are at some particular location WT, but we didn't really exploit any information that comes from the path that we took to get here that will reveal some information about our training point. So we can implement this idea using a variation on a class of information theoretic bounds that were introduced just earlier this year by Stank and now. Consider a super sample Z tilde, which is of size 2n. So here we have two rows, each row is of length n. And our training set S is now constructed by choosing entries from this super sample. So at each column I, we choose one of the 2 points from the 2 sample, and we put it into our training set. And we choose uniformly at random. You will be our index now, indicating which of the 2 samples we chose. So UI at column I will be equal to 1 if our training sample S contains the element Z1I, and will be equal to 2 other I's. The conditional mutual formation of our training algorithm with respect to this data distribution D is then equal to this conditional mutual formation. So CMI stands for conditional mutual formation, but it also stands for this particular conditional mutual formation where we're conditioning on this super sample. So now instead of measuring just mutual information between W and the training set S, we'll be measuring mutual information between W and our training, index to the training set, or index to the super sample that gives us a training set, conditioned on the super sample. Does it make sense? No questions, so I'll move on.
I missed what was the ZIIIJ.
Say it again?
You said consider a super sample. I'm not sure what is inside this super sample. Like, what are the Z?
Super sample is just independent samples, ID samples from our data distribution. But it's instead of just considering n samples, we consider double the amount.
Okay, so we have 2n examples which are independent from our training set.
Yeah, yes, thank you. So in this original CMI paper, the authors show that this conditional mutual information, CMI, is bounded above by n, the number of training samples, log k, where k is kind of a more general version of the super sample. So here I only have 2 rows, but you could have actually k rows and extend this. In contrast, mutual information between W and S can be infinite. We show that CMI is actually always bounded by the mutual information. So here is the Zhuno-Ginsky theorem that I presented multiple times, bounding the expected generalization error. Here is the CMI bound. So it bounds the expected generalization error in terms of this conditional mutual information that conditions on the super sample. And what we show is the following. So let J be chosen independently at random from 1 to n. So just as before, J will be indexing which training sample we will be holding out, or will, holding out from the prior. And we show that expected generalization error can be bounded in terms of this quantity, which it's actually a disintegrated version of mutual information. So if I were to move this expectation inside, then I could be, then I would have the usual conditional mutual information, but I took it out. And so I have mutual information that's that has access to the super sample Z tilde and also this index into my training set. And I'm measuring the mutual information between my weights W and the index UJ instead. Okay, so in the previous bounds, I showed a version where at the Jth location in our training set, we are potentially resampling the training point, right? So the prior had access to all the training points except for the one at the Jth location. In this case, instead of thinking that I can resample any training point in the Jth location, I'll be able to resample only from the ones in my super sample. And this quantity is always actually upper bounded by the original term appearing in the sphere. Does it kind of make sense, or was it confusing?
Yes. If you, I guess, if in the end you get that this, disintegrated version gives you tighter bounds, that makes a lot of sense.
Yeah. So it does give much tighter bounds. So if you were to apply this bound for longitudinal dynamics, then the individual sample bound, so this bound that I just presented here, leads to 2 sample incoherence. So it's measuring, the bound depends on the difference between the gradient on the Z1 J training point, or sorry, the point in the super sample versus the gradient on the other point, right? So now if I go back to this super sample, I chose some, let's say I chose J equals the second column. Now I'm measuring how different the gradient is on this point versus this point, because that's the only one that my prior doesn't have access to. That was here. So this 2 sample incoherence will now be appearing in the bounds. So conditioning on all but the Jth entry in the training set, how much information do weights WT reveal about which of the 2 examples, Z1J and Z2J, belongs in S. So a naive approach could be assigning equal probability, right? So with equal probability, our training set may contain this example or this example. And if we have no further information, for example, at the beginning of training, just at initialization, that's all we can do. And in that case, we incur in the bound the full penalty that depends on the L2 norm of this 2 sample incoherence. And here's an idea that we exploit in our NERDS paper. After observing the full path up to time t, so from the weights from W from time 1 to t minus 1, predicting identity of the Jth entry can be viewed as binary classification problem. Informally, the lower the risk of this prediction, the tighter the bound, reducing the penalty of the two-sample coherence. So if we have access to everything that happened at the time t and the path we took, we can greatly reduce our uncertainty about which of the 2 points in the supersample actually belong in our training set. Does anyone have any questions?
I don't see questions in the chat right now, but don't be shy, people, if you have questions.
I'm not sure about the binary classification problem. What are you classifying? Either if it's 1 or 2?
Yeah, essentially, if it's 1 or 2. If it's like this example or this example that appears in our training set.
But isn't it chosen randomly? The one?
No, so yeah, I should probably have made it more clear and highlighted more, but the sample that's missing to the prior, that the prior doesn't have access to, it's consistent, it's the same one during the whole training run. So in the bounds, when we are taking this expectation, we are averaging over the index j, but every run, j index is fixed. Okay.
So basically, it means that like you have already seen like z1j or z2j previously, so you're kind of like.
Yeah. So you the posterior has seen z1j, well, sj essentially, right? The posterior has seen which of the training sample has appeared, but what the prior gets access to, it's only these noisy steps,
right.
W1 to WT. Okay. Which are prepared with extra Gaussian noise. So you don't have the full information, which of the examples belongs to the training set, but you have access to these noisy iterates that reveal information.
I see. So the intuition is that like if you have reached this particular point, you may have information to recover from which example you learned that that weights.
Yes, exactly.
Okay. Thank you very much.
I'm happy that people are understanding. Okay, so here are the plots of the bound. On the x-axis of the training epochs, so we run the training for a very long time, way more than needed to converge. The red one is one of the state-of-the-art bounds that were published earlier this year. The green line is our bound from last year's NIRPS paper, the one that I presented earlier that did not use a super sample. And the blue line is our current bound. So initially, we have a little bit more penalty because we have very little information on which of the 2 examples from the super sample was in the training set. But as we train for longer and longer, the penalty really diminishes and plateaus. It doesn't grow anymore. So especially, there's a huge difference when training on CFAR, SCNN on CFAR. So this new bound, it plateaus, stops growing, versus the other ones just explode during training time. And that's really one of the disadvantages of using these bounds that break down mutual information for overall to each step, mutual information in each step, because they grow with training time. But our new bound seems to plateau. Okay, so to summarize, I discussed some barriers to explaining generalization in deep learning. I introduced mutual information bounds on expected generalization and described some applications to understanding stochastic gradient and longitudinal dynamics. In Pensi et al. Paper, mutual information between the training data S and the weights learned by stochastic gradient and longitudinal dynamics is bounded above by information leaked at each iteration of training. In our bounds, they're distribution dependent because we use samples. So I explained that distribution independent bounds and information leakage yield vacuous bounds in standard regimes, especially in deep learning, and introduced distribution dependence via KL bounds and data dependent priors. And I also presented some empirical findings demonstrating that these data dependent bounds produce much tighter estimates. So gradient and coherence term was much smaller compared to gradient norms or upper bounds on the Lipschitz constant. And It produces fairly loose bounds still, but not that loose bounds for the first iterations of training. And conditional mutual information bounds tighten it up even further. So of course, there is more work needed to understand the limits of mutual information based on explanations of stochastic gradient and longitudinal dynamics, and tighten up this analysis even further by not breaking it down iteratively, but thinking about better ways to exploit the path that's been taken. Okay, thank you very much.